What's good, y'all? Welcome back to another video. Today we're going to be going over some trig stuff again. I had a student send in some worksheets that we went over together, and I just wanted to bring them over here just to show you guys kind of the more solving equation side of trig, the verifying identities type of thing, using those trig identities to solve equations, things like that. So without further ado, let's get right to it. All right, question 1 here. Says cosine of x times tangent x plus cotangent x. Now, if I could give you guys any advice when it comes to questions like this, what I would say is anytime you have tangent or cotangent or secant and cosecant, turn it into cosine and sine if cosine and sine are also a part of your equation. The reason why is because it's setting you up for opportunities to simplify things. If we have everything in a bunch of different terms, it's very hard to see how everything can be condensed. But if we have everything looking like each other, it's a lot easier to make sense of everything. So I'm gonna rewrite this. It's cosine x times, this is sine over cosine, so sine x over cosine x plus cotangent, it's just the same thing but flipped over, so cosine x over sine x. Next thing I'm gonna do here is I'm gonna multiply out. Well, cosine x and then sine x over cosine x, we'll notice this is actually going to cancel out, just giving me sine x. And then cosine x times cosine x is going to be cosine squared x over sine x. All right, next thing I need to do here is combine like terms. So, well, not combine like terms, but I want to combine these two terms together. So in order to do that, I have to add. Well, in order to add fractions, I need a common denominator. Sine x is the same thing as sine over 1. So for me to find a common denominator, I'm going to multiply this thing by sine x over sine x. The reason why is because I want to have a common denominator, sine x. That's going to turn this thing into sine x, well, sine squared x over sine x. Then this is going to combine together now. I can add this together as sine squared x plus cosine squared x all over sine x. Just kind of like a little bit of advice here. Anytime you see sine squared, cosine squared, either adding to each other or plus 1, instantly think Pythagorean identities. In this case, sine squared x plus cosine squared x is equal to 1. So this is 1 over sine x, aka cosecant x, giving us the fully simplified version right there. All right, next question is sine x plus cosine x cotangent x. So same thing as last time here. I'm seeing sine, I'm seeing cosine, I'm seeing cotangent. Let me just rewrite this as cosine x over tangent x. Oh, whoa, tripping. Over sine x. From here, just multiply out. So I'm going to get sine x plus cosine squared x over sine x. And this is looking mad familiar to the last one. And it should, because it actually is the exact same thing from here on out. So I'm going to multiply the top and the bottom by sine x. Okay, that's going to also give me, aka sine squared x over sine x. Okay, then I get sine squared x plus cosine squared x over sine x. Okay, that whole thing just equals 1 over sine x. And once again, we got cosecant x. And that wraps it up for this one as well. All right, keep it moving. All right, next one I got is cosecant x sine x plus cotangent squared x. All right, first thing I'm noticing, again, just like the ones before, cosecant, I'm gonna rewrite it in terms of sine. So 1 over sine x times sine x plus cotangent squared x. Now 1 over sine x times sine x is the same thing as sine over sine x, which ends up equaling just 1. And then right here, I'm seeing 1 plus something squared. Automatically, I'm thinking Pythagorean identity, in case it actually is, equaling cosecant squared x. Now, a couple things I wanted to bring up here. For one, cosecant x sine x, I automatically changed cosecant because of, like I said, I always want to put it in terms of sine. But why didn't I change cotangent? Well, the reason why is because of this idea of pattern recognition. You're going to start recognizing, and this is something that I recommend for you guys as well, is anytime you see 1 plus something minus 1 or something squared in trig, we should automatically start thinking, okay, Pythagorean identity is probably at play. There are so many identities and so many patterns that you're going to have to memorize, which is very hard. But if we can kind of just start gaining this pattern recognition of maybe not knowing exactly what identity it is, but knowing something has to work out here, that's going to start building this like thought process that we need to solve these more efficiently. I automatically, anytime I see something squared, I'm thinking Pythagorean identity. So in my mind, I'm like, I could turn this into cosine over sine, something like that, right? But why would I do that if I know that there's a possibility that this thing reduces to something using an identity? So I weighed off on this one, fix this one, and in this case, it works out. So just that thought process, right, is gonna help us when it comes to proving certain identities and things like that, proving something is equal to something in trig or whatever it is just recognizing these things and maybe waiting off on changing this, knowing that there's a possibility that this all reduces out that way. But on to the next one. Cosine x times 1 plus tangent squared x. All right, this is actually a prime example of what I was talking about last time. I see a 1 and I see something squared. Automatically, I'm thinking Pythagorean identity. So if you don't have these completely memorized, this is when you pull out your identity paper, look at it. We know that it's gonna be some type of Pythagorean identity because it has the 1 and the squared. It ends up being secant squared in this case. All right, now in order to combine, I'm gonna rewrite this as 1 over cosine squared. Okay, these are gonna cross reduce. This is gonna become 1. This is just gonna become a singular cosine, making this equal to 1 over cosine x, which is equal to secant x. That would be the final answer there. On to the next. All right, these are a little bit different. Now we're actually solving equations rather than simplifying expressions. So I have sine x, cosine x, minus 3 cosine x equals 0. So now that it's set equal to something, I actually have to solve this thing. So the first thing I'm noticing is I have cosine in both terms. So the same way we distribute in the parentheses, like we multiply everything by the value outside the parentheses, I can divide out like this, almost like reverse order. So in other words, I'm going to undistribute the cosine from both terms, and that's going to give me sine x minus 3 is equal to 0. Now this should somewhat look familiar, especially if you've taken like an Algebra 1 class, because this looks like some type of factored form where I set both of these separately equal to 0 and solve, and that is actually exactly what I'm about to do here. I'm going to have cosine x equals 0, and then sine x minus 3 is equal to 0. Okay, so cosine x equals 0. Well, what I'm trying to think of is I'm trying to think of when cosine is equal to 0. So pull up my little unit circle here. Well, cosine is equal to 0 whenever x is equal to 0. That's going to be right here and here. Notice that is the same thing as pi over 2. And then also 3 pi over 2. But the fact that I'm not bounded here, meaning it's not saying 0 to 2 pi, I'm going to do something a little bit different than naming them, because then that means I'm going to name all of them. Notice how the difference from this one to this one's pi. So what I'm going to do is I'm going to do plus pi k. And what that essentially means is, hey, it's pi over 2 plus pi multiplied by whatever integer you want to multiply it by, because no matter what, if I just keep on going around in a loop like this, it's going to always give me an answer to cosine 0. So that would be my answer over here. Over here, I'm gonna get sine x is equal to, well, let me just add 3 to both sides. Sine x is equal to 3. Well, sine is never gonna equal 3 on the unit circle because the maximum value is 1. So actually, I don't even care about this one, leaving me with just this as my answer to this equation. Okay. 2 sine cubed x is equal to sine x. Again, I gotta solve here. First thing I'm gonna do is I'm gonna subtract sine from both sides. So 2 sine cubed x minus sine x is equal to 0. Now I'm gonna do the same thing that I did on that last one. I'm gonna take out a sine. Since they both have sine x terms, that's gonna end up giving me 2 sine squared x minus 1 is equal to 0. And then from here, I'm just gonna set both of these equal to 0 again. So sine x is equal to 0 as one of them. And my other one's gonna be 2 sine squared x minus 1 is equal to 0. Well, this one, let's just start here. Sine is always equal to 0 now that I'm dealing with my y terms. Over here and over here. And so right here is like 2 pi or that 0 form. This is pi. I'm gonna put this one because I don't want to put 2 pi or I don't want to put 0. So pi and then just k. And the reason why is because pi plus pi k is the same thing as just pi k. It's just the same exact thing because me multiplying this by whatever integer is gonna get me to pi plus pi k. So that's kind of redundant. I don't need it. So this is gonna be one of my answers. This one over here, I'm gonna add 1 to both sides. That's gonna give me 2 sine squared is equal to 1. I'm gonna divide by 2. Okay. Let me get some space back up here. I'm gonna divide by 2. That's gonna give me sine squared is equal to 1/2. Let me take the square root of both sides. That's gonna give me sine is equal to, well, the square root of 1 is just 1. Square root of 2 is just square root of 2. You're not technically supposed to have a radical in the denominator, so what I'm gonna do is I'm gonna rationalize my denominator by multiplying by root 2 and root 2. And that's gonna give me x, in this case, is equal to root 2 over 2, right? That's all I'm looking at here. Now, also notice this is gonna be plus or minus because I did take the square root of both sides. That gives me basically free reign here. So now what I'm thinking of is when is it root 2 over 2? Well, that's a special angle, specifically 45 degrees or pi over 4. So if sine x is equal to root 2 over 2, I know that this is gonna equal pi over 4 plus pi over 2k this time. And the reason why is because it's plus or minus. So that means that this is a possibility, this is a possibility, and this is a possibility. And if you look at this angle right here, this is that 90 degrees to get from this side to this side. So I have to add 90 degrees or pi over 2 radians each time, giving me my pi over 2k. All right, next one. I got tangent squared x equals 1. Well, I'm just gonna solve. Take the square root of both sides. I'm gonna get tangent x is equal to plus or minus 1 because the square root of 1 is 1. But now it gives me plus or minus as possibilities. And now I gotta think about when is tangent x equal to 1? Well, tangent is sine over cosine, and now I'm thinking on the unit circle, essentially when is sine and cosine the same thing? Again, that is gonna be pi over 4, right? Because root 2 over 2. And then root 2 over 2 is the same for sine and cosine. So in this case, it's gonna be pi over 4. And then since it's plus or minus, it doesn't really matter. So pi over 4 plus pi over 2, okay, once again. All right, last two questions here are kind of on the same idea, but now I am given an interval of 0 to 2 pi, which changes things up a little bit. So for this first one, I'm given cosine to the 4th x plus cosine squared x minus 2 is equal to 0. And now I just got to solve this. Now notice this looks a lot like a trinomial, except the fact that it's to the 4th degree and also the fact that this is trig. So what I'm going to do is I'm going to do a u substitution. In other words, what I'm going to do is I'm going to replace cosine squared x with u. So that allows me to rewrite this equation as u squared plus u minus 2 is equal to 0. Now from here, this is just basic algebra, right? I'm just going to factor this thing. What multiplies to negative 2 but adds to 1? Well, that's going to be 2 and negative 1. So I get u plus 2, u minus 1 is equal to 0. And now what I'm going to do is I'm going to resubstitute back cosine squared into both of these. So cosine squared x plus 2 is equal to 0. And cosine squared x minus 1 is equal to 0. Now let me just solve both of these separately. This one's going to be cosine squared x is equal to negative 2 after I subtract 2 from both sides. Take the square root. I'm going to get cosine x is equal to square root of negative 2. Okay. And then here, this is actually not even a thing, so I don't even have to worry about that. It's imaginary. So then all I worry about here is just cosine squared x is equal to 1. So cosine, take the square root of both sides. Cosine of x is equal to plus or minus 1. So when is cosine x equal to plus or minus 1? It's when my x values are positive and negative 1. So that's going to be right here and right here. And essentially that's the same thing as pi and 2 pi. And 0 as well, because of the interval between 0 and 2 pi, and it was closed interval, which means that both of these values are also included. So the answer then in that case is going to be pi, 2 pi, and 0, because those are all, in this case, within this realm. All right, last question here. So first thing I'm going to do is I'm going to subtract 1. That's going to give me 4 sine squared x equals 3. Next, I'm going to divide both sides by 4. That's going to give me sine squared x equals 3/4. Now I have to get rid of that square, so I'm going to take the square root of both sides. That's going to give me sine x is equal to plus or minus the square root of 3 over 2. Look at that, it's a special angle right there. So what angle is that? The way that I like to think about it is 3, 2, 1, 1, 2, 3. Sine is the second one, so 1, 2, 3. This is the same thing as 60 degrees, or pi over 3. And the fact that I'm dealing with all 4 quadrants, well, in this case, what I'd have to do is I have to do, this one's my first quadrant, so let me just write that there, pi over 3. My second quadrant is 180 minus theta, the value that we're given, so pi minus pi over 3. That's 3 pi over 3 minus pi over 3, which is 2 pi over 3. The third quadrant is going to be theta plus pi in that case, so 3 pi over 3 plus pi over 3, which is 4 pi over 3. And that final answer there, the one in the fourth quadrant, is going to be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, giving me 5 pi over 3. And that's it, guys. If you want questions walkthrough similar to this, again, this was something that I worked on with the student during a tutoring lesson. Always feel free to just drop it in the comments, and then I can work through questions just like this just for you guys. Like, subscribe, and I'll see you on the next one. And as always, take care. Peace out.